Welcome to the collisions topic. Thus far, we've only considered situations where the objects are somewhat ideal. So, for example, in motion, we use Newton's laws, which requires that we assume we're dealing with a particle-like object. And in forces, we always only looked at the free body diagram on one object at a time. In reality, we deal with objects that are all different kinds of shapes, and more often than not, with systems that contain more than one moving object. So for collisions, that's something of a requirement, really. So knowing how to predict the behavior of these systems can come in very handy. So for example, predicting the path of where the pieces of a meteor that exploded in our atmosphere will land, or predicting how much fuel a rocket ship will need to get out of the atmosphere, which is actually a much more complicated procedure than it sounds. So in this topic, we'll look at how to describe and predict the behavior of somewhat less than ideal cases of strangely shaped objects and systems that consist of more than one object. In this particular video, we'll look at step 1, which is how to find the center of mass of the system. So we know when we throw a solid particle-like object, like a tennis ball, it will behave like a projectile, and we can describe its motion. If we know its initial conditions, we can figure out how high and how far it will go by using the equations of motion and by using Newton's laws. And we do this by assuming that the object is particle-like. So what that means is that we assume that all of the mass of that object is concentrated into a single point in the center. But what about objects like a tennis racket? So if we throw a tennis racket, how will it behave, and can we predict it? And in order for us to predict its motion using Newton, we know that we have to be able to assume that it's particle-like and that all its mass can be found in a single point. And we can do that. This point we call the center of mass. And in all of our work so far, when we predict the motion of roller coasters or trains or cars, we've been unconsciously using the center of mass for our calculations. When we draw free body diagrams, we're drawing the forces acting on the center of mass. So what we will do in this video is to formalize this notion and how we find it. So how do we find it? There are several ways to find the center of mass, or this single point that represents the mass of the whole system. And the first of those is using symmetry. So if we have a symmetrical object, so that is an object that is symmetrical in both shape and density, or symmetrical in mass, then we can easily say that the center of mass lies on the axis of symmetry. So for example, with these three shapes, with a circle we know that we have an infinite number of axes of symmetry, all of which pass through the center. So I've just drawn 2 in here, but there lies the center of mass. Likewise with a rectangle and with a triangle, the center of mass lies on the axes of symmetry of the system. But what about our tennis racket? So, the tennis racket has a shape that is symmetrical along the y-axis or the vertical axis, but not along the x-axis, and it also doesn't have a uniform density. So what we do is that we split the racket into shapes or parts that we can find both the horizontal and vertical axes of symmetry, and we assume that each part has a uniform density. So, as should now be familiar to you, the first thing that I will do is to draw a diagram and define my coordinate system, and then put my object on it. We can then define our axes of symmetry of each of our parts and locate their centers of mass. That gives us 3 centers of mass. The first is located at a position x1, y1, and so on for 2 and 3. So now, in order to find the center of mass of our tennis racket, we need to know how to find the center of mass of a system with more than one object. So we'll start with the 1D case. Here we have 2 bodies of mass 1 in the red and mass 2 in the yellow, located at position 1 and position 2. I'll use a simple example of a seesaw with each of our masses on either end. What we're looking for with the center of mass is the point to place the fulcrum of this seesaw so that our seesaw is stationary. If our masses are equal, then the balance point must be exactly in the middle of those 2 masses. But if one mass is heavier than the other, then we need to shift the fulcrum closer to that heavier mass. So you can experiment with this using a ruler and various different objects, and I've included a video with a suggested classroom activity at the bottom of this page. Using our knowledge of forces, we know that the ruler will not tip as long as the forces down on each side of the fulcrum are the same. So from this force analysis, we can derive our formula to find the location of the center of mass. However, in order to derive this formula, we need to know about something called the torque, which is the rotational force. And we don't encounter the torque until the next topic, so for now I will just give the equation and we'll derive it later. For a two-body system, the center of mass is given by the formula the mass of object 1 times its location plus the mass of object 2 times its location, divided by the total mass of the system, which in this case would be mass 1 plus mass 2. This is a very general formula. So if we add more objects to the system, we still use exactly the same technique. And our general formula that we derive from that analysis is that the center of mass of a system with many bodies is equal to the sum of each of the individual masses multiplied by their location, divided by the total mass of the system. So in 2 dimensions, we use exactly the same idea and exactly the same formula. So our center of mass, written as the vector r, is equal to the sum of the mass of each particle multiplied by its location, divided by the total mass of the system. In this case, our location is given by the 2-dimensional vector r, which has an x and a y component. So we can find the center of mass of the system by finding the center of mass of each of the x and y components using that 1-dimensional formula, and the same goes for 3D. So now we know how to find the center of mass of a system with more than one component. We can apply it to our tennis racket. We have assumed a uniform density for each part, and that has allowed us to calculate the center of mass of each component. And using our 1-dimensional equations, we can calculate the center of mass for the x direction and the y direction, and that allows us to find the total center of mass. We could make our life easier by choosing the y-axis as the vertical axis of symmetry, and then we would again just have a 1-dimensional problem in the y direction. So in summary, we know that the center of mass of an object or a system obeys the laws of motion. So for example, the projectile motion example I showed you in the first slide. For objects with symmetry, the center of mass lies on the axis of symmetry. And when I say symmetrical objects, I mean objects with a symmetrical distribution of mass. For systems of objects, in a 1-dimensional case, the center of mass is equal to the sum of the mass of each of those objects times their location, divided by the total mass of the system. And to find the center of mass of 2 or 3-dimensional systems, we simply need to find the center of mass of each of their components. I've included a couple of questions below this video, and I reckon once you can do those, you've got the center of mass down pat.